So Bhavna, should we start?
Who am I speaking to? Oh, Manjunath, are you here?
Manjunath.
Oh, sorry. Yeah. I'm
I didn't know.
yes.
I didn't know if you had joined, so I was waiting for you. Okay.
Oh, is it? Okay. No. I joined a couple of minutes ago. Yeah.
Okay. Yeah. Great. So let's start.
Yeah.
Manjunath, shall I go ahead and introduce Shruti? Do you want to just say a few quick lines before I?
No. You are the person to do it.
Okay.
Go ahead.
Okay, great. Thank you all for coming. We're here for Shruti Shekhar's Thesis Defense. Uh, a very warm welcome to all of you and to Professor Srinivas Vivek, who's here from IIIT Bangalore. He's one of the reviewers for Shruti's thesis. So Shruti today is going to talk to us about her very exciting work in the broad area of non-malleable codes and leakage resilient secret sharing schemes. So she's been doing a lot of interesting work. She's had a very interesting set of papers in her during her PhD, and she's worked on a very broad set of topics and published in broad set of venues. And one of the things that really stands out about Shruti is that she's extremely open to ideas, to people, to thoughts, to suggestions, and so on. And that makes it, it's one of those very underrated research skills. And I think that's really come in handy. And it's of course been fantastic working with her, and I'm excited to listen to her talk now on near optimal non-malleable codes and leakage resilient secret sharing schemes. Shruti, the floor is yours.
Thank you. Thank you, Bhavna. So I'm happy to be talking today. It's always any link to ISC is always welcome, and this happens to be my defense. So today specifically, I'm going to. So my thesis is titled Near Optimal Non-Malleable Codes and Leakage Resilient Secret Sharing Schemes, as you can see. And today I'll focus on particularly one of the primitives of the two, and that's going to be non-malleable codes. So give me 1 second. Yeah, so particularly in today's talk, I'll focus on this recent paper called Rate 1/3 Non-Malleable Codes. It is to appear at Stock 2022, and it's a joint work with my wonderful co-authors, Devesh Agarwal, Bhavna Kanukriti, Maciej Bremski, and Sai Lakshmi Bhavna Bhattu. So particularly, I'll first start with telling you what non-malleable codes are and why they are exciting. And we'll head into see, what are the important parameters associated with it, what is the state of art with respect to it, and eventually I'll get to how we build them. So let's start. First, what are non-malleable codes? So they were introduced by Zimbowski, Petrzak, and Wicks in ITCS 2010, and they are particularly a specific kind of coding schemes, which, as the standard notation goes, consists of this process called encoding. It takes in a message M, and there is this algorithm encode, which additionally can take in some uniformly random generated coins. So it's called a randomized algorithm for it, and you encode the message to some code word C. Now, the setup or the kind of adversarial model you consider for non-malleable codes is that such a code word, wherever it is prone to some form of adversarial tampering. By which I mean, we'll come to specifically what kind of tampering is allowed and all. For now, think of it like some function is applied to C, and it is modified to some C prime. And you will decode it. So decode is the process that helps you recover back the message from this code word. And the kind of guarantee that I seek from non-malleable codes, which is called non-malleability, is that either this recovered M prime, the tampered version, is same as the original message M, which means I have managed to correct all the errors that are created in the code and recover my original message, which is good. But if not, the guarantee that I seek is that this recovered M prime is actually independent of M. So in a while, we'll see how formally you capture independence, but intuitively what it is trying to capture is that either you're able to rectify all the errors and get back the original choice of message, which is desirable. But if too much tampering has happened and a lot of information from the code word is lost, in this scenario, you cannot hope to recover. And for crypto setups and applications, as we'll see later, it's useful to have a notion that this M prime is unrelated to M. It doesn't have any information about the original message M. Okay, so before I tell you more of a motivation for considering them and application for it, let's try to formalize what I mean by this independence. Okay, so I just bring back the same setup. We have this encode algorithm. This is the code word. And to formalize this, I'm going to specifically now focus on the tampering model that throughout this talk we are going to be interested in. And this particularly looks at the code word as two parts. So this is some left part, and this is some right part. And it's called L and R. And we allow the adversary to pick functions F1 and F2, where F1 acts on L. So L prime is F1 of L, R prime is F2 of R. These functions explicitly act on each of the paths separately, but themselves could do anything with the specific part of the code word. So they are arbitrary functions. And once this tampering is done, as before, you decode and recover the M prime. So this whole process leads to this M prime, and I capture it with this distribution, which I called tamper. So if you notice, the randomness for this distribution depends on whatever the encode process uses. And this distribution depends on the choice of the message gem and the functions F1 and F2 that the adversary would have picked. Okay, so what is the goal? We want to capture what I mean by calling or saying that this distribution is independent of M. This is what I want to capture. And this is done by something called as simulation paradigm in crypto. So informally, what it means is that I want to, in turn, say that there exists some other distribution, which I call simulator. And this only depends on the choice of functions F1 and F2, not on the message M. And it is such that for any choice of message that I could have started with, the tamper random variable ends up being close to the simulator. Okay, so the closeness here and throughout the talk, whenever I mention, is going to be in statistical distance sense. So for any two distributions, the statistical distance is half of the L1 norm. And this is the closeness that I'm going to be talking about. So to summarize, what this definition is trying to say is that if I capture the actual tampering that's happening by this distribution, it so happens that I can in fact define another distribution which only depends on the tampering function choice and not on the message. And this turns out to be close to this actual tamper experiment for every choice of the message. So this basically tells me that this independence is captured basically through this definition. Okay, so this is how we define non-malleable codes. I didn't mention in the beginning of the talk, but at any instance, if you have any questions, feel free to stop me right there, and I'd be happy to answer in between the talk. Okay, so where are non-malleable codes useful? Let's look at a motivating application to sort of stress more on why this definition is useful. So one setup, we could take any crypto system, particularly let's say I take a signature scheme, okay? So digital signature scheme, particularly you have a key K, and the signing algorithm takes in some message and generates signatures. The goal of such process on the whole is that whenever an adversary observes multiple message signature pairs or sees this process run, then at the end, the adversary should not be able to forge any additional signatures on an unknown message for which it has not seen. So this is basically an authentication system that provides security against forgery. But a key assumption here is that this key remains uniformly random. The adversary does not know it, and nothing additionally is observed. So what happens in a setup where, let's say, the adversary does some form of external tampering to the key and is able to modify it to some K prime? Well, these class of attacks are what are known as related key attacks. And here, in fact, the adversary can make use of the additional information, which are basically signatures on this K prime, and break the whole scheme. And in fact, one such example is where it's shown that RSA signature fails under random faults that are introduced into computations. This is a work by Bonet, DeMillo, and Lipton as early as Eurocrypt 97. So to handle such attacks, one solution offered is by non-malleable codes that we have defined. How do we make use of this in the setup? Instead of storing the key directly, I'll encode it and put the code word in this strip. So now if the adversary actually tampers, note that you would tamper the code word and recover some K prime. So what are the two situations that can arise? Either I would correct and ensure that the K prime is same as K, in which case it's like a regular signature scheme. The adversary only gets to observe signatures on K and we are good. We can use the standard security. But if not, this provides a guarantee that this K prime is actually independent of K. And this independence crucially tells you that the adversary doesn't see any useful information dependent on the original key. And so related key attack is really not possible anymore. So this is just a motivating instance to show you where this kind of a definition helps in the crypto setup. And indeed, there are several applications that non-malleable codes have. Just to list a few, they've been applied to non-malleable commitments, non-malleable secret sharing, domain extension of non-malleable encryption, privacy amplification, and more recently to black box 4-round pairwise multi-party computation and plain model. So these are just a list of few applications where non-malleable codes have been useful. So the next natural question to ask is, given the setup and having seen that there are several applications, what are the parameters of interest with respect to these objects? And as you would guess, there are two key aspects. So the first is something we've been seeing and talking about, which is the tampering model. So there are several tampering models that have been considered in literature, but like I said, we'll be focusing on one specific model, and I'll mention briefly about it. The second sort of rate parameter that is of importance is the rate of the scheme. So rate typically measures how much redundancy you introduced in the code, and you don't want a scheme where the message is blown up to too long in order to provide this protection. So let's look at these one at a time. The tampering family, as I even provided the definition for, is in what we call as the T-split state or split state model. So more generally, if I have to tell you what this model is, I showed you for two parts of the code word. More generally, this is called a T-split state family. And here you view the code word as stored into T separate chunks. And you allow the adversary to modify each chunk arbitrarily, but independent of each other. Okay, so this is generally called T-split state model, and T can vary from 2 all the way up to N, where N is the size of the code word. And this is a formal description of it. So you have each function acting on every block. And as you would notice, lower the value of the T is, more powerful the adversary is. So basically, T equals 2 is the strongest in this setup. Why is T equals 1 not possible? This is something which is kind of easy to see in the setup. So T equals 1 is a scenario where you allow arbitrary tampering of the whole code word. And if you note here that because the decode process is something the adversary can run, there's no secret involved in the decode process, right? So an adversary or a function which is tampering the C could simply decode the C and then just add, so this is the actual message M, and it could just add some string to it, let's say 1, and re-encode it. So this tampering will always tamper my message into a related one, which is message added with something. And such tampering in this strong setup of information theoretic world, you cannot hope to provide security against. So this was shown, in fact, in the first paper itself where it was introduced. So arbitrary tampering is out of the window for the whole code word. So the next sort of strongest setup here is for T equals 2, where you view the code word into 2 parts. And that's precisely the model we'll be focusing on today. So that's with respect to the tampering model. Coming to the rate, rate of the scheme formally is the ratio of the message length to the code word length. And as I said, this shows that it measures the redundancy that you introduce into the message when you encode it. And it's preferred that you have higher rate of the scheme. So basically, you don't want to increase the size of the code word by too much. So having said that, one of the long-standing open problems in this realm has been to build optimal rate non-malleable codes for the strongest tampering model in this setup, which is two split state model. Great. So that's the task we have set to achieve. And let's see what has been done in the literature. So let's take a glimpse of the prior works. The first natural question is, if we want to build optimal rate codes, we have to start with the question of what is the optimal achievable rate. And this was precisely answered by this work of Cherrachi and Guruswamy at ITCS 2014. So they showed a feasibility result that for this T-split state family, the best achievable rate is 1 minus 1 over T. So particularly for the two split state family, this would mean, so T equals 2. If I substitute, this would mean half is the best achievable rate. Okay, so this is the goal you set to achieve. And until this realm, there was not even an explicit code for non-malleable codes in the two split state model. And this was started around the same time with by Zimbowski, Kazan, and Obrimsky. At Crypto 2013, they gave the first explicit construction, but this worked only for 1-bit messages. So they gave a non-malleable code for two split state model, but that worked for only 1-bit messages. And even for that, they required well, the construction was nice, elegant, but the proof style itself was quite complex, even for this. So, and the rate that the scheme achieved was omega of 1 over n, where n is the code word length. So it's an inverse polynomial rate. So, and subsequently, the next year, Agarwal, Dodis, and Lovett, in this beautiful work at Stock 2014, they gave a first explicit construction extending the scheme of DKO to build for arbitrary messages. So they use similar technique in their construction, but in order to make it work for arbitrary messages, the proof became even more non-trivial, and they used techniques from additive combinatorics. So there went a lot of analysis to build these schemes, and it achieved a rate of, as you can see, omega of 1 over n to the 4/5. So this is an optimized rate obtained in a sequence of 3 works. Okay, so at this point, if we saw, we have an explicit construction for the two split state codes. But if you see, like I said, the proof techniques involved in these works were quite non-trivial to analyze, and hence also to optimize further. So the sort of next question the community posed was, can we find alternate routes for building these codes? Potentially something that led to getting better rates. And this is somewhat what was initiated by the subsequent work by Cherrachi and Guruswamy, once again around the same time. And they built these non-malleable codes by establishing and introducing the connect with these tools called non-malleable extractors. So I'm not going to be talking about them, but on the whole, this led to a sequence of several beautiful works, and it sort of culminated in this work by Shinli in 2019, which gave, amongst all these lines of work, the best rate, which was omega of log n over log n. So again, if you look at it, the connection itself was quite elegant, and it did give a new potential route, and it led to an improvement in the rate. But they required building these non-malleable extractors, which in themselves were quite complex primitives. So they needed inherently several complicated steps to build. And once again, it hit a roadblock where we could not figure out how to improve parameters beyond this. And so again, there was a need for new techniques, and this led to another line of sort of techniques that were introduced by, once again, this beautiful work by Agarwal, Dodis, Kazan, and Obrimsky at Stock 2015. So they established a new kind of proof technique in this realm, which they call non-malleable reductions. And while this work in itself did not have a constant rate, they conjectured it. The actual code that they built had omega of 1 over n to the omega 1 rate. But this line of constructions is indeed what led to the most recent work, which was by Agarwal and Obrimsky in last year Fox. And through this route, they were able to build, in fact, the first constant rate non-malleable codes. So this is quite exciting improvement in this realm. But if you notice, the rate here of their construction was, in fact, 1 over 1.5 million, which is quite a big rate. And not only that, once again, this line of construction were quite complex, and the proofs had several steps. Indeed, it led to blow up of parameters at every stage. And when we went into analyzing them, it had inherent limitations in improving parameters. So we are again back to the stage where we were asking questions of newer, simpler routes to get better rates from these schemes and better constant rates. So this is what we managed to do in this work, where we improved this rate to a near optimal one. We built the first one-third non-malleable code schemes for the two-split state model. So on hindsight, this is really a sequence of works. It's established through a new sort of route to build them via what we call rate and non-malleability amplifiers. We'll see in a bit what I mean by them. But this sort of connect was established through a sequence of works by two subset of authors from here. And as an additional advantage of this construction, not only did we get a rate improvement, but this was quite a simple construction, and the proof is also non-tedious as opposed to prior works. So this is going to be my goal, to sort of give you a highlight of how we build them, how we managed to get this rate through this work. So I think I have managed to hopefully get you to understand what non-malleable codes are and set the goal of what we strive to achieve. And now we are ready to see the construction, but now would be a good point for me to stop in case anybody has questions about either the definition or any of the prior works. Okay, great. So if not, let's proceed. Let's see a glimpse of how we build these. So before we head into seeing the construction, we need building blocks, and actually just two building blocks, which are quite simple to see. So the first is some form of an authentication mechanism. So particularly, we need an information theoretic one-time message authentication code. So just like we saw some signature schemes before, right? In the same context, this is a much simpler scheme. It has just a single MAC algorithm. It takes in some authentication key and signs the message, generating the tag T. Informally, the guarantee you want is that only one-time security, which means that if an adversary sees a message tag pair, for another message, you should not be able to forge signatures in the information theoretic sense. So formally, what it means is for any m not equals n prime and t prime, the probability of m comma t being a valid message pair, conditioned on m prime t prime being a valid message pair, is low. So this is some error you bounded by. So this is the first tool we need, which are information theoretic one-time maps. They're quite simple to build. And in fact, you can build them where the key and the tags are quite short, as we would use in our construction. We'll see later. Okay, so the second building block sort of that we need is the strong randomness extractors. So they're primitives that were introduced by Nissan and Zuckerman in 1996. And they're very cool objects in the pseudo-randomness literature, which essentially take in any source. Basically, it comes from a distribution that's only known to have high enough entropy. And the goal of these primitives has been to extract out pure randomness from such entropic sources. So particularly, this extractor algorithm takes in string W that's drawn from an entropic distribution. And with the help of an additional short uniform string, which is called a seed, it's able to generate a Y. And the property that it satisfies is that if you look at this output distribution, it looks close to uniform. Once again, the closeness is in the statistical distance sense. It looks close to uniform, even given this short seed that I generated, along with potentially some extra leakage information that I might get on the source. So this is like, think of it like some function applied on W. The only condition I need is that the entropy of W conditioned on this leakage should still remain high. Okay, as long as that's guaranteed, given all this extra information, the extractor output looks uniform. So this is the second tool we need. And in addition to this, as I sort of use the terminology, what we build is a rate or non-malleability amplifier. So as the amplifier suggests, we indeed use underlyingly some other two-split state non-malleable code. And potentially this could be any of the prior constructions that I listed with a poorer rate. And what we managed to do is amplify the rate of that scheme to get this rate 1/3, and sort of use the non-malleability of something we encode using that underlying scheme. So indeed, if we have to make rate benefits, we can only use this underlying scheme to encode something short. And that's what we would do in our scheme. Okay, so in that sense is what I meant, that we are actually going to build rate and non-malleability amplifiers. So with that, I have set the stage to tell you how the construction works. But before we head into looking at the full-blown construction, let's look at this warm-up construction to understand every component and how the non-malleability works. So let's start. The goal is to encode this message M. And first natural thing one would do is we want to encode it in a way that it hides the message to begin with. So what tool do we have at hand for it? The extractors. So what do? We generate a source W, seed S, and we XOR the message with the extractor output. So this is the way we would hide it. And now as two states, I'm going to, in one state, going to give out the source out in the open. And in the other state, I'm going to give out the ciphertext C. Okay, so since I'm giving them out and open for security reasons we'll see later, I also would need to have some authentication guarantees for them. So what I would do is generate MAC keys, KW and KC, and I would generate signatures for them. And these signatures also I can append with the ciphertext in W. Okay, so these are the two states. Now, what is the remaining information that I need to provide to be able to recover my message? The seed S and these authentication keys, right? If I pass them on, then I have all the information needed to decode the message. But notice that we cannot directly pass them on. We do want to get some non-malleability guarantees in the end. So if we give out everything in clear, you cannot hope for it. And here is where we have the underlying non-malleable code at hand. So like I said, the authentication keys are going to be short because Macs support it. And likewise, extractors use quite short seeds. So we exploit this feature of both these schemes, and we'll use the underlying non-malleable code to encode these short messages. And this gives us the two states L and R from the scheme, which will output as the two remaining states. Okay, so this is what I mean by the 4-state scheme. I look at the code word as these 4 parts, and instead of, we will allow the adversary to tamper each of these parts separately. Okay, so this is my encoding scheme, where I take the message, hide it using the extractor, and output the ciphertext. I give the source that was used to generate the extractor output also out in clear in a separate state. And in addition, I'll give the 2 states that encode the seed and the authentication key. Okay, so that's all my scheme is. And let's have it here. So on a very high level, let's look at why such a scheme would give non-malleability guarantees. And hopefully, like I sort of give a glimpse of how the proof works for at least the post-state model. So recall the adversary is allowed to tamper every part separately. So the C and the tag is one state, and the adversary can tamper it separately. F2 acts on W and TW, F3 acts on R, and F4 acts on L. And if you remember from the non-malleability definition, to capture this, what is the ultimate goal? We want to build some form of a distribution, which is the simulator, that only depends on the function choice and not on the message. And this should, in a sense, capture the tampering experiment, right? So it was close to the actual tampering experiment. How do we build the simulator? Well, the natural thing is we are building a non-malleability amplifier. So I'm going to use the underlying simulator for it, which is now direct to C. So there are these 2 functions, F3 and F4, that directly act on L and R. And I can just, they fit in the split state model perfectly. So I'll just output I'll just use the underlying simulator and get these S prime, KW prime, and KC prime. Now, what are the 2 cases, if you recall, that could happen in the non-malleability case? One is if the tampered message is retained to be same as the original. If not, you have a guarantee that it's independent. So we'll analyze each of these cases separately. And let's start with the sort of simpler case to see what happens when it's same. Okay, so the seed is retained to be same and the authentication keys are the same. And here, a natural thing to see is we can use the max security, which will give a guarantee that if at all now my ciphertext is modified or my source is modified. So if C prime is not equal C or W prime is not equal to W, then the max security would directly imply that you should output a special symbol called abort, which means that you don't, it's not a valid code word. You detect and abort that. Why is this? Because if in either of the case that the tags verified, the message authentication code verified, then it would lead to a forgery from the adversary, and that defies the security of the MAC. So in this case, it's clear you cannot modify the C and W whenever the authentication keys are same. So in other words, there would be no tampering, and hence you should output the same message M. Okay, so great. When it is same, everything is fine. We can use the max security and things look good. But if not, now I have to rely on the independence of S prime. And this is where the extractors kick in and they help us out. So I want to capture the fact that the M prime now that I output is independent of the original message M, right? And if I look at the extractor security, it provides a guarantee that the extractor outputs look uniform, given the seed, of course, but additionally, there was this leverage of leaking something on the source. If you recall, there was a function of W that I could output. And here is where I can use the fact that S prime is independent of the seed S. So if I really look at this extractor output, this is a function of the actual W. S prime is something independent. And this I can capture as this leakage. So the length of this extractor output is something that I can tolerate and guarantee extractor security holds. So given this information, my extractor output will look uniform. And if you see, this is exactly the information that will give you the tampered message M prime. So particularly M prime is extractor output on W prime S prime XOR with C prime. Okay, so because of this independence, you directly imply that the M prime that I recover is independent of the message M. And this is all I had set the goal to be, right? So I have amplified the non-malleability guarantee of the seed to the non-malleability guarantee of the whole message M prime at the end. So this is the high-level structure of how the simulator works in the scenario where everything is in a separate state, things are nice, you don't have cross correlations. So it's a 4-state model. But if you look at our 2-state scheme, which is the end goal, it's exactly this construction, but now we club the R or merge the R with the ciphertext C and its tag, and merge L along with the source and its tag. And now we allow the adversary to tamper all of them together. So naturally, you have given more power to the adversary, and this is a much more related tampering. And this leads to complications, as you would guess. It's no longer easy to make clean arguments in the independent scenario. So while there are several challenges, one of the prime challenge that I want to point at here is that we land at trouble when we are trying to prove independence. It's tricky. And particularly the problem is in using extractor security. So this is something that I would be able to tell you because we just saw in what form we use extractor security when things are nice in the 4-state world. And that sort of argument would not work here for the following reason. If you look at this extractor on W prime and S prime, which I had output as an auxiliary information or a function of W, that no longer can happen here because it, of course, depends on S prime. And this S prime, it at least depends on the tampering functions, right? And particularly if you see the tampering function that acts on this state, F2, that depends on the ciphertext C, because you're no longer tampering R independent of it. And because of this dependence, in turn, this depends on the actual extractor output on W and S. And this is a dependence you cannot handle extractor security with. If you give some information that depends on the source string and the extractor output, you can actually break the extractor security. So we can no longer use the extractor security the way we were able to in the 4-state scenario. So this poses one of the main challenges in the proof. And particularly, like the only thing I'll focus on to give a highlight of what we do in the proof is I'll just focus on the independence case, and particularly I can tell you a glimpse of how we overcome this problem. So like I said, we have this dependence of the S prime on the extractor output, and hence on the auxiliary information that I need to give. And I want to resolve this problem. So this we do by some form of a careful analysis of capturing this correlation and somewhat breaking it using a Markov style argument. Okay, so I'll not go too much into the detail of the proof, but I at least wanted to give you a glimpse of what I mean by this Markov style argument. So particularly, what is the reason for all this correlation? If you see, like I said, the dependence is on through this ciphertext C, right, which depends on the original message M. So as a first step, I'm going to consider a scenario where the C is no longer in picture. So I'll consider some random C tilde, and I will generate everything I'm supposed to besides this in the tampering as before. So S prime now only depends on C tilde. So the green I'm using to denote all information that's dependent on the C tilde. So S prime is not dependent on C anymore, and hence this information, if you see, is no longer dependent on the extractor output. So first observation here is that this random C, the extractor of W prime S prime, and the extractor of WS, which is the original output, they form a Markov chain. This is somewhat of a simple thing to see here because you're taking a fresh random C tilde. And the second thing to note, which is the whole point of starting with this scenario, is I have removed the dependence on the actual ciphertext and hence on the extractor. So I can now use the regular extractor security. Things are good here. And this is what I do. I'll use the extractor security and I have the guarantee that it looks close to uniform given this information. But this is not going to help me give what is the actual distribution I need, right? I need to bring back the dependence on the message or bring back the original ciphertext. And this is where we use a nice property that Markov chains guarantee, that if I have these two steps, we can actually show that the C tilde, when I condition on XOR of that and the extractor output, which is this part of the Markov chain, if I condition that the XOR of them is actually some message M, then this distribution is still close to uniform, given still the extractor output on W prime and S prime. So this is a nice property that one could show if you have such a condition on Markov chains. And in some sense, we have segregated the argument into several steps and first removed the dependence that created the problem and then brought back that dependence, but in a somewhat of a limited sense through this. So this is all I wanted to sort of highlight on what is the challenge in proving such a thing in the two-split state world. But of course, there are like several complications that we have to handle and carefully analyze in the proof. But I'm not going to be getting into details of that today. So to summarize, what I just showed you was our work, which gave this 1/3 rate non-malleable code in the two-state model. And particularly, it was built on this new route that we took, which was of building rate and non-malleability amplifiers, as opposed to prior schemes. So if I have to really categorize them, these two schemes were built on something called using inner product extractors. These came from non-malleable extractors, and these schemes used non-malleable reduction. So our route used rate and non-malleability amplifiers. I somewhat showed you a proof sketch of a toy example or the start point of the solution, and pointed at some of the challenges we faced when we actually headed into the final two-split state world. For more details, you could find the paper online. And that's pretty much all I had to say about this paper. But just to end, I wanted to give a brief overview of what I did in my thesis overall. So my thesis is comprised of actually 4 works, 2 of which capture about the first primitive, which is leakage, delay, and secret sharing. This is something I didn't speak of today. And the other 2 capture non-malleable codes, which is what I just told you about. And broadly, these 2 primitives deal with a class of attacks in crypto, which are quite neatly tied. So non-malleable codes deal with something called tampering attacks, which we saw, and leakage-resilient secret sharing schemes deal with something called as leakage attacks. They are also some form of thing that standard security doesn't capture, and you need to build schemes that provide resilience against these attacks. Moreover, in building optimal things, so like non-malleable codes, where my goal was to build optimal rate codes, leakage resilient, my goal was to build optimal share size schemes, and the kind of techniques involved in both these realms are quite connected from the pseudo-randomness literature particularly. So that is basically the goal, or what I did in my thesis. Yeah, so that's all I had to tell you today. So thank you. I'd be happy to take any questions.
Hi, Shruti. Thanks for the talk. Does anybody have any questions? Okay. So I think the next step is for the faculty. Yeah, does anybody have a question? Please just unmute and ask. So I think the next step is for the committee to meet Shruti alone.
For acknowledgements, they could join back.
So no, so we can actually move to perhaps. So Manjunath, would it be okay if we met on Google Talk?
It's fine. Yeah. Or we can. Yeah. Either way is fine.
So we can just leave this on here. Sorry. Okay. So the examiner. Wait.
Have questions, everyone will be interested. So
yeah, so Srinivas says he has questions that everybody can listen to, and he doesn't need a private session. Like he's okay. So Manjunath, is that fine?
No, I mean there is always the question session. This can go on. There is supposed to be an in-camera session. If you want to say that this is not enough, she has to write 4 more papers or something. So
yeah, so then we can just skip that, right? Yeah. Okay.
Okay.
So, yeah.
No, when we have public question session is already there, so one can continue with this for as long as you want, and then we can move to the private session, which can be as short as you wish.
Yeah, I think.
yeah.
No, I think your suggestion is that there doesn't have to be a private session at all. Right?
No, man, I don't want to bypass your rules. If it is okay,
no.
not to
I'm
have,
asking Manjunath. So if it's not required, then we don't have to. Okay, fine. So for now, Srinivas, just go ahead and ask your questions, and then we'll see.
Yeah. Hello, Shruti. Yeah, thanks for the talk. So I have some very minor comments. Probably you would have seen my report, but what I would be more interested in the future work. In case you get time to work on this, so what do you think that you want to address?
One of the things that I'd be interested in is to see, more application of non-malleable codes. So of course, like one obvious goal here is that I still got only near optimal. Its final step is to get half rate codes.
So how close do you think are you to getting the rate half?
With these kind of, so the right now, whatever is the proof strategy, this is somewhat the best you could do. So for half, you would need to come up with potentially new techniques, and that would be a separate work of its own. But these techniques, this is the best that I think one could hope for. So we could not improve beyond this from this kind of technique style. But yeah, more applications would be one thing that I would be interested in, because non-malleable codes are already they have several applications, but in the realm of this domain, like seeing further applications is of interest. And likewise, leakage and secret sharing schemes, they play a role in other works like MPC or several other applications. So there, one of the obvious goals is considering several leakage models, and there actually there's more widespread in terms of the models that you could consider, adversarial models. So yeah, some questions are open out there as well. So
so when you say optimal share size, again, it's in the split mode model, right? I'm talking about leakage resilient sharing schemes. right?
Yes.
So I think for probing security, it's obviously the share size, they're already optimal, right? They're just as long as the word size. But it's just in one is going to
That's
be
not okay. So that is not known before. Like, so one of the, if you look at the one where you just independently leak, their optimal share size, which is basically you would expect the share size to be same as message length. Yeah. That was not known. So one of the works that I have is to match that for the leakage with length setting. You know it for regular sharing schemes, but for leakage length secret sharing, we did not know of that. So that is one of the works. The other is that you don't know of it when you consider stronger leakage models. So when you allow that kind of setting where you have adaptive leakage, or you combine some shares and allow joint leakage, there you don't have the optimal share size. So in fact, there we get some constant blow up in the message length. And we don't have scheme which gives you share size equals the message length. So yeah, even getting a constant blow up was not known before. So in that model, and that's precisely the other work that I have.
And then what do you think that whether this will extend to the continual leakage model? I guess you're looking at the bounded leakage, right?
Yes, bounded leakage. Continual leakage model, of course, there are several works in that model. Once again, like, optimizing the share size is one problem you could look at. In the computational world, of course, you have schemes that already do it. But in the information theoretic sense and using light tools in the continuous leakage model, we don't know. So that's also one open problem if you want to optimize share size there.
So, and if I say that I want to implement whatever you have proposed on a microcontroller, so you think that it's feasible and it will run in realistic time? I know it's not the main focus of your thesis, but what do you think? That would you be interested to collaborate with a crypto engineer who wants to implement this?
One of the key things, if you see in all these schemes, is right, they use randomness extractors. So I don't know how you would run, like, I don't know much about, what goes into practically implementing those particularly. Other components, I would say, are somewhat lightweight, or you could do it. But randomness extractors, I don't know.
Yeah, it can be very efficiently implemented, yes.
Okay.
I was more interested to know the extractors, but it's okay, yeah.
Yeah.
Right. And I think one more question. So, one part deals non-malleable codes deal with tampering, right? Other with leakages, protecting against leakages, and there are already actually realistic attacks. So where they have tried to exploit both the faults, right? And then and also the leakages, through, say, power analysis. So this combined attacks, combination of fault attacks and the leakage attacks. So they are already like practical attacks on practical systems to have practical on implementation to have really demonstrated the practicality of this. So you think that there is scope to combine these two?
Combining these two actually is there, which is something I didn't mention. So if you look at non-malleable codes, which is one primitive, we can even tolerate leakage on top of it. So you can allow leakage from the code word also. So our code itself directly achieves some form of leakage resilience actually already. So in some sense, like, you have features combining both. Likewise, in the secret sharing setting, so this actually I added in the revision of the thesis. The other review asked me to somewhat have a connection of this form. And in the leakage resilience setting, also there are schemes which combine leakage resilience and non-malleability of the secret sharing. So there are schemes which tolerate both in the secret sharing setup. And in fact, like, we have applications of the leakage resilience secret sharing to building such schemes where you get non-malleability as well.
Okay. Okay. Yeah, that sounds very interesting. Thanks.
Thank you.
So, whatever Professor Bhavana and Professor Manjunath.
No, so we'll just do a quick meeting with, so Srinivas, Manjunath, Shruti, and I can just have a quick meeting. Shruti, would you be able to very quickly paste a Google Meet link?
Yeah, sure. Should I just send it here?
You can just send it here.
Bhavana, the simplest is visually we just ask others to leave and we can continue on this, right?
We can do that also. Yeah, we can do that also.
Either way is okay with me.
Okay, yeah. So Shruti, we can do that.
Yeah, sure. Yeah. In which case, like, I think people can, I don't know how to message and let them know, rejoin for the acknowledgement session. So yeah.
Okay.
That's the only.
If you want to join for acknowledgements.
Oh, is there such a thing? Okay. Usually we just kick them out, but yeah. But okay. No. In that case, have a separate meeting. It's okay.
Have a separate link. Can you just send us on this chat itself? You can just send a link.
Sure. I'll just do it. Yeah. Give me 1 second.
You can come back after.
Ma'am, shall I stop the recording?
Yes, sir. That would be fine.
Yeah, fine.
Thank you.